Oskar Mencer, the founder of Maxeler Technologies, and one of the main feature that we are just setting up a contract to have some of your machines in our Wigner GPU laboratory. I hope this is on the very way, so sooner we will have it. It's okay like that. So we will have it ready to work in our group. So please speak about the things and everything around these issues. Thank you very much.
Thank you, Balázs. Jonapod to everybody in Budapest. Thank you so much for inviting me to talk about static data flow. It is exciting to have this talk, especially on the GPU day, because it allows me to provide a balance and a counterpoint to the tremendous push in the direction of GPUs, and to show what other opportunities and other types of technologies there are out there. So I titled this 20 years of static data flow because it turns out just a few months ago, we also had 20 years of the first lecture that I gave that inspired the creation of Maxeler technologies. This was 2001, just after I got my PhD at Stanford, and I was invited to give a talk here. You can see I was still employed at Lucent, at Bell Labs, and started as a young academic at Imperial College in London. You can see here, 2001, 20 years ago, the underlying technology that made it possible to explore new architectures, to explore new ways of computing, were the up-and-coming chips, where you could change the circuits underneath. You can adapt the structure of the computer to the structure of the problem that you're trying to compute. And there were a lot of consequences of that possibility, both on the architecture side, as well as on the number representation side, on the way that we represent information, on the way that we represent data. And you have to keep in mind, this is 20 years ago, so the whole focus on data was not yet popular in the computing industry. This was kind of a very different way of thinking about things back then, while today it's a very common and very appreciative way of thinking about computing. To go back a little bit further, if I had named my talk 1,000 years of static data flow, it wouldn't have attracted that much interest. So I was hiding it by saying 20 years, but really I'm going back much further than that. You can see here Euclid's Elements, and you can see the importance of representation. This was one of the most advanced scientific documents of the time. Euclid was explaining how to calculate the sides of a triangle. And it was really complicated. You can see the text in the middle is Euclid's explanation. And then the text on the boundary, the stuff that goes around the middle, that are commentaries, explanations, because people didn't really understand what he means. So they said what he really means is the one side and the other side. Of course, today we teach this to school children. And we have a notation, we have a representation of the problem that makes it 1,000 times easier to understand what the problem is and to solve it. So the way we represent things is a measure of complexity. It's a measure of how much effort is needed to compute it. And of course, with modern notation, a squared plus b squared equals c squared, we can do that now. Fast forward to 1971, again, a very important year. This is now 50 years ago. You can see a microprocessor, the Intel 4004, a milestone in computing, introduced just at the same time as we lost the gold standard for the US dollar. And we can see here that computation is dominated by transistors. There are a few connections in here, but most importantly, the whole effort here was on arithmetic, on storage, on transistors that do something. If we go forward even a tiny little bit to 1 micrometer, then 32 nanometers, 10 nanometers, we see that the transistor is shrinking while the wires cannot shrink. And it's particularly easy to explain this in a physics context, because if you shrink the wire, you increase resistance. And if you increase resistance, the thing gets hotter and hotter all the way to catching fire and exploding. And one of the early lessons that I was taught by a fellow CEO of another company, when I just started Maxeler, was that you should never set your customer's data center on fire. He said, once you do that, it is impossible to recover the relationship with the customer. And so I took that very, very close to my heart. And indeed, we did not burn down any data centers in our 20 years of existence, which I am very proud of. But moreover, we took it to heart that wires are more important than transistors. And what do we do on the wires? We move data on wires. So if we reduce the movement of data, the requirement for moving data, we are reducing power consumption, we are reducing energy, we are improving speed per unit of energy. And that is really the goal that I set out, which is very different from most other people. And so the solution that we came up with also is very, very different from a GPU. The solution here is based on the principle that we want to compute as fast as possible at as low an energy as possible. To quote the previous speaker, it's a hunt for optimality. So how did we do that? In 2003, we started with a Maxeler Static Dataflow model, meaning that we cast the flow of data into a static structure where we can minimize the travel distance of all the data items. The data moves continuously and drives the computation. A side effect here is that we don't have a halting problem. So the whole concept around computer science, the problem created by sequential computing, by the Turing machine, goes away. And in fact, I believe that the last machine that Turing built was actually going in this direction. But of course, it's very hard to find out these days. So we are looking to find the optimal solution for any specific problem and formulate it as a flow problem. We don't want to waste any silicon. We don't want to waste clock cycles. We want to make the entire system predictable in terms of throughput and latency, and minimize the energy for moving data. So we create static Dataflow kernels, which are assemblies of arithmetic units. So think of a Dataflow kernel as just a bunch of adders and multipliers. But they're connected statically in a rigid connection that is set at the beginning when we start to run the program. And it's set in particular in a way to minimize data movement. So that's a fundamentally different way to compute. It has impacts on complexity theory. It has impacts on time it takes to do a computation, the space it takes to do computation. And it's generally a very uncomfortable place to be because at least 20 years ago, it was going against the grain of where computer science was going. And so it can be a pretty interesting experience to be doing that in an industry that was going completely the other way. Looking further into history, this is one of my favorite passages as well that I got from Professor Paul Kelly at Imperial, where John Eckert is describing his experience, where he's reiterating, meaning that he said it many times before, but he's reiterating that all the arguments for parallel operations are only valid provided one applies them to the steps which the built-in or wired-in programming of the machine operates. Any steps which are programmed by the operator who sets up the machine should be set up only in a serial fashion. He's setting out that any parallelism is undesired. It has been shown over and over again that any departure from this procedure results in a system which is much too complicated to use. What he fails to say is that the insistence on sequentiality of the description results in a system that is 10 to 100 times more expensive in operation. It is 10 to 100 times more expensive to pay for the electricity bill. And at the same time, if you have cloud providers, it provides 10 to 100 times more revenue to anybody renting you computers for running your sequential program. So that creates a conflict between revenue and opportunity, between effort needed and cost of operationally running a computer system. And within that conflict, we see the different computing solutions arise. Since this is a talk in Hungary, of course, I could not refrain from bringing up János von Neumann, who in 1946 clearly identified that this is going to be a problem. He says we are forced to recognize the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. So words from history again, wise words from history, that forced to recognize really means that he doesn't want to, right? He doesn't want to recognize, but he's forced to recognize that in the interest of efficiency, one would have to create a hierarchy of memories. And that is about location of data, where the data is and how it goes from where it is to where it needs to go. So here is what happened a few years later. As a result, we ended up with cache hierarchies, with memories, with disks, and solid-state disks, and the hierarchy between them, where at 2 gigahertz, a load, an assembly instruction load, can take 0.5 nanoseconds all the way to 150 million nanoseconds. And the programmer has no way, no idea if it is going to take 0.5 or 150 million. It is really, really difficult. You have to study the actual computer system that your program runs on, which a programmer doesn't want to do. A programmer wants to write a program that runs on any computer. If it runs on any computer, our predictability of how long it will run is 0. It's worse than 0. It can be catastrophic. It can run fast on one computer and millions of times slower on the other computer. How would you ever optimize a computer program if you don't know how long it's going to run in the first place? So clearly, optimization is not possible within such a framework. And so that's what we're trying to solve. The problem is even worse. The problem goes a lot worse than that, because convenience has infiltrated everything. And here is a real customer project where a customer came to us and said, our program runs too slow, it takes 100 times too long, it takes days to compute something, and we really need it in minutes or an hour or two. And so we looked at it and we saw that the customer is using a database and SQL. and running SQL queries in order to do a computation that reports data to the legislation, and it's doing that too slowly. It took 114 seconds for a sub-problem to be computed. We rewrote the whole program in Python and used something really revolutionary. We used a file to store the data. Our customer could not believe that it is possible to store data in a file, because they believed that it needs to be stored in a database, as they were told by IBM. As we were doing this project, we showed that you can run in 1 second in Python what took them 114 seconds to run on an IBM database. Maybe not as a consequence of our project, but a few weeks later, I read in the newspapers that IBM and my customer were proud to announce a number that was close to $1 billion that my customer paid to IBM to buy the next generation of IBM systems in order to run their activities. So this is the real world in which we operate, just to kind of balance the excitement over efficiency and running things quickly. The difference between these is driving a Prius. If you work with Python, this is not a Ferrari yet, right? This is just a Prius, but the world is operating like this. The world is operating on a 3-year-old's tricycle. And so the problems of the real world are much bigger than just science and technology. There are real conflicts and real large money movements involved between banks and large technology companies. And so this is just an example to show how far one can go. Back to science, what is the optimal way of doing it? So Python, we know, is pretty good. You use a file, that's fantastic. That already would get you quite far. You can build custom hardware. And here, I like to bring up the theorem from Kolmogorov, who described that there is an optimal program given a language. So given a language L, there is an optimal size program to generate any sequence of numbers, to generate any computing result. And that number of kind of the size of that program is very similar, of course, to Shannon's information theory concepts. And then Kolmogorov came up with this at about the same time. Shannon was a little bit earlier, but this is by many people considered a corollary of Shannon's information theory. But it's much more useful to us because it also says that if I don't know language L, I can optimize infinitely, possibly. My question is, what is the optimal language? Find the optimal language to describe a particular computing problem to make it compute as fast as possible. While for a particular language, there is a limit. If we can pick the language, we have a huge amount of opportunity. So here is a language that we picked. We picked a language of graphs because a structure of many compute problems can naturally be expressed as a data flow graph. And so this is a graph where each dot in this graph is an arithmetic unit. It's an ALU, it's an adder or a multiplier or something like that. We see here almost 5,000 of these connected in a very, very specific way are solving the acoustic wave equation. So this is solving a partial differential equation. It's one time step of solving that partial differential equation with a finite difference method. It's a 3D solver. So you have a 3-dimensional space. You have a wave going through that space or multiple waves. And this is simulating one time step. So you're iterating data. It goes up at the top. it flows through and comes out at the bottom. We know exactly how long that is going to take. We know exactly how much data we have if we assume a certain discretization. And so we can compute exactly how long it will take to simulate this acoustic wave equation. Because this graph is static and the connections are static, we are calling this static data flow. There are many nice features of this. One of the nasty features is how the hell are you going to describe this? How are you going to program a computer that needs this as its input? And so starting from this point, we were focusing on how to program static data flow computers. And that may seem like a very, very hard thing. But the key thing with hard things is to not worry about it and just go do it. My friend here was clearly told by his colleagues that you cannot ride your bicycle and carry your car across town. And he said, watch me. I'm going to take my bicycle, I'm going to put the car on top, I'm going to drive it across town. And here he is doing it. So one shouldn't let the impossibility of a statement try to stop oneself. So here it is. We decided to use the then most popular language out there. At the time, 17 years ago or so, this was Java. And we embedded a semantic environment for describing static data flow structures into the Java language. We had to modify the virtual machine a little bit. But essentially, we created variables, data flow engine variables, DFE vars, that allow the specification of expressions. These expressions can be transferred into expression graphs, which are then converted to data flow graphs. The nice thing here is that as you're programming on the left in Java, you can see your data flow graph on the right inside of the same IDE. And so it's kind of connecting the programmer with the reality of what he's creating. Our goal was to make data flow programming fun. And it was inspired by the then CEO of Tesco, who of course said that all of his products have to be easy to use, desirable, and affordable. And so we set out to create the most efficient, the optimal computing structure for any compute problem and make it as easy as possible to program it. As easy as possible doesn't mean that it's easy, but it's as easy as possible. And we can argue if the desirable and affordable part has been met, but at least we had the best intentions and we tried to make it as easy as possible. So then looking back at how do we construct the language? How do we think about constructing the language? And then so here I'm really relying on a neighbor of Hungary here, Ludwig Wittgenstein, who was born in Austro-Hungary, of course, at the time. And he proclaimed that the limits of my language mean the limits of my world, which was an inspiring statement for me for a long time. The data flow corollary for this is that, of course, the limits of my programming language mean the limits of what I can optimize. If my programming language doesn't describe something, I cannot optimize that. So my programming language needs to describe data movement and allow me to reason about distance of data movement, because it's the distance that sets the speed and the energy that is needed. So we are trying to describe data movement. How are we doing that? We're doing that with a data flow program on the left, where every line of the program corresponds to a certain resource, to a certain asset, to a certain space on the chip. We are computing in space, and storing our data in time, which is exactly the opposite of what a sequential computer does. A sequential computer computes in time, sequentially, and stores the data in space, in memory. Here, the arithmetic units are organized in space, and the data flows in through these ports, like X here at the top. You go at the top of the picture and you go down, that is where the data streams in time. A physics connection here is essentially we're doing an FFT on our computer program, and we're computing in the other domain. And in the other domain, suddenly our computational problem is transformed, easier and much more obvious to optimize. So this is a very familiar concept in physics, but applied to computer programs. This is one of the things that I'm teaching in my EE 382 lectures at Stanford to complement the mainstream computer science direction that of course still widely insists on sequentiality of programming. One nice feature of that is shown here. So when you write a program on area, or when your program executes in area, every line of your program can be annotated with the number of resources that it's using. So if you have a fixed number of resources, which is always the case in a finite world as we have it, you can now annotate each line in your program with the number of resources it takes. In fact, you can also say how long it will take for the data to flow through that particular line of code. So we also need a structure, and due to practicality reasons, we of course need to take our static data flow and put it somewhere. So we put our static data flow kernels into chips called FPGAs, because we simply couldn't afford to make ASICs. If we could make special purpose chips, that would have been the preferred solution. So we started off with the lowest entry point here and connected these chips with memory on the one side, large amounts of memory, and with PCI Express or InfiniBand on the other side, and tied them into general purpose Linux systems where we run some software that manages the flow of data between the various cards in the system. So this is the general architecture of our data flow system, which was deployed in many different types of applications. An interesting application here that I like to mention, because this talk is in Hungary, of course, is the Kalman filter. I'm always inspired by walking past Kalman's house at Lake Balaton. And so I like to use this to demonstrate abstraction possibility on top of data flow. Here we implemented a Kalman filter state machine with an abstraction on top of the data flow abstraction. Because we are in Java, we can create hierarchies of objects, and we can build vector and matrix objects. And now we are talking about algebra, and we can do transformations and manage large and complex data structures in a hierarchical way that makes it much more appealing to describe very complex problems. So the complexity here is managed by a hierarchy of objects that are very nice to describe in an object-oriented language. Here is the graph that comes out. Again, it would be close to impossible to imagine anyone implementing this with classic hardware approaches, where you would write Verilog to describe all of these different nodes and how they're interconnected. One would clearly go crazy trying to write the code for all of the lines that connect the dots here. especially if there's a little change in the arithmetic, a little change in the equations, one would have to create all of these different connections from scratch again. So really, the automation of a static data flow programming environment is critical to be able to do this. So one question that I get a lot is, how do you deal with the concept of loops? How do you create dependencies? How do you have loop-carried dependencies, as computer science puts it? And so I had to make an animation to show how this works. And there's also the code that you have to write below that to show that in just a few lines of code, you can replace the left code, which is pseudocode in traditional programming, with a loop-carried dependency. And the type of data flow code that one would have to write to create such a dependency. And the animation here shows how the data flows through. So the different colors represent different vectors. So you have a blue vector, an orange vector, a green vector, and a red vector. And you can see that there are essentially 4 versions of this loop being merged into one, because we have 4 stages in our loop. And we can easily create 4 of these computations in a row, computing at the same time. So this structure will compute 4 of these loops at the same time. It computes one, produce the 4 results. And as you can see, all of the stages of the pipeline are used at all points in time, because we've essentially used data parallelism to fill the pipe and to get the loop done. So this shows we can do data dependencies, we can do loops, all good. However, it does take effort. So here, this is just to mention a talk that was given by my PhD advisor at Stanford, Professor Mike Flynn. That was a little while ago already, in which he talks about the great debate from 1967, where he was present, in which Gene Amdahl and Slotnick were arguing about the parallel approach. Gene Amdahl being on Eckert's line of parallel programming is too difficult. And he says the parallel approach to computing does require that some original thinking be done about numerical analysis and data management in order to secure efficient use. However, in an environment which has represented the absence of the need to think as the highest virtue, this is a decided disadvantage. What is that environment that Slotnick is talking about? That environment is called computer science today. Computer science has represented the absence of the need to think as the highest virtue. And that's how we arrive at sequential programming. That's how we arrive at databases. That's how we arrived at SQL. That's also how we arrive at tremendous amount of inefficiency in computing, where things take way too long, way longer than they should. Now, it's easy and good to talk about efficiency, but sometimes one has to put actions where the words are. And so we built a complete line of supercomputing equipment with CPUs, with an appliance that had static data flow cards only in it, connected with InfiniBand, that allowed us to balance the amount of static data flow cards with the amount of CPUs that they're connected to. And then on the right side, a networking appliance, which was arising because with static data flow, we have predictable latency, and networking, of course, benefits greatly from predictable latency. We have workstations, we have rack level solutions. So there's a whole set of products that had to be developed in order to create a computing environment. And then figuring out how to export a computer system to China, which was maybe more difficult than the previous things I was talking about, but we succeeded with that. And here is the outcome of the machine that we sent to Beijing, comparing a climate model, one of the most important computations for humanity today, climate modeling laid out by John von Neumann, of course, as one of the key challenges early on, we are still struggling with. And this was a measurement done completely without Maxeler's involvement. The university, Tsinghua University in Beijing, has measured and shown that they have a Tianhe 1A computer with dual GPU nodes. And the dual GPU nodes were compared to a node with Maxeler cards that you can see on the top. And you can see that there is a speed difference of 14 times on the speed side, but also 9x in terms of energy, which is the cost of operating the computer system. So how is that possible? How is it possible to beat the world's fastest computer at the time by 14x on speed and 9x on energy? Or paraphrased from Feynman's lectures on computation, you can look at the theory of this, and it says, in theory, a computing unit can be constructed which uses no energy. So computing itself doesn't need to use energy from a physics perspective. It is only when information is lost or when information is moved that energy really needs to be expanded. And so by minimizing the amount of flow of data, the amount of distance that the data travels across all the data, in essence, by solving 1 trillion traveling salesman problems, we managed to minimize the amount of energy used for the computation and also the time. Here is a machine built for the UK government. We built the machine. It was obviously here supported by the people in government and by the scientific community until it hit the UK government laboratory where it was installed in Daresbury, where the software team looked at this machine and said, well, we're not touching this. This is not a computer. It doesn't operate the way we are used to. And we don't care if it is 100 times better or faster than anything else. We are not going to touch it. And so they didn't. It was standing there next to an IBM Blue Gene, which was a nice photo op, of course, for our rack. But the internal team refused to touch it. Or as recently a professor of physics in Hungary told me, he's not going to burn a PhD student on using such a machine because it would clearly destroy the person. The machine was used, however, by a lot of researchers outside of that government laboratory, and we had some really nice results for the Human Brain Project in Europe. So several good publications came out of this, and there were plenty of users, but also plenty of people scared and upset at how different it is and how much it doesn't fit in with what they need to do. Funded by the European Union a little bit after that, we made some progress on computing many different high-performance computing applications. My most favorite application here was quantum chromodynamics, where we showed that we can implement quantum chromodynamics a lot faster and so contribute to the most fundamental of all physics simulations, the simulation of quarks inside of the elementary particles. But there are several other applications here that resulted in a machine being installed in Jülich in Germany and being used by the community there. So quickly, how do we migrate applications to static data flow? Now that we know that it is there, we need to look at the entire application and draw what I call a loop flow graph, which is not a traditional way of drawing computation, where every box represents a loop, and the thickness of the arrows represent how much data is being moved. The reason for this is that we need to make a cut, a min cut of that graph meaning a separation of that loop flow graph into stuff that is going to run on the static data flow side, and 90% of the computation which remains on the CPU side. So we are only migrating small parts of the computation. We're generating an architecture. This is an architecture diagram of how the data flows between the static data flow kernels. And it's critical to draw both the loop flow graph as well as the architecture diagram before starting to implement things, which is not a common and appreciated activity for computer scientists. Computer scientists prefer text. They don't like to draw pictures. And so there was a struggle over the years to get computer scientists to draw the picture first before starting to implement. Yet another lesson on how different professions operate. Engineering likes to draw pictures. Computer science likes to write text. Having to do both complicates things with static data flow. Here's the quantum chromodynamics, again, another architecture. You can see spinners, gauges, clovers, very exciting things on the physics side, and how they're implemented in a static data flow architecture. Since we're running out of time a little bit, I'm going to move forward a little bit faster. I mentioned one also needs to consider number representations, and especially how we change, adapt the representation of numbers to the actual requirements of the computation. From a floating point perspective, we're looking at exponents and mantissa and the different values throughout a lifetime of a variable inside of a computer program. And we build tools in order to monitor these. So given that we have a whole other way of doing computing, visualizations are critical here. And so here you have a tool and how the exponent for a particular variable varies over time. And then looking at the computation in space, here's the aerial view of one of the most popular computations these days, neural networks. Everybody wants to do AI and neural networks. And so here is the implementation of a fully connected neural network on an FPGA split across 3 chips with the different colors representing different static data flow kernels. I mentioned that because the colors represent the staticness between the different static kernels. It's of course dynamic. And that's important because these static kernels are connected to dynamic memory and to a dynamic PCI Express bus. So some dynamicism is really required. And on the engineering side, I guess we would call this a globally asynchronous, locally synchronous architecture, a GALS architecture. And we like to visualize this as an output of the compiler. You just compile your program and you get these pretty pictures that you can actually then study to look at where your inefficiencies may lie. One of the questions asked, another question is, can we do sparse matrices? And so the answer here is yes, published in IEEE Micro in maybe a decade ago. This was a project done with Stanford University and Schlumberger. And you can see here speedup is achieved for static sparse matrices. Very important here beyond that is to say, okay, computation is one thing, but how about data and networking, storage and networking? So it's really important to think big and reconsider, restructure, change how we approach not just computation, but also storage on the one side and networking on the other side. So all 3 components need to be considered when looking at applications. What did we achieve over the last 20 years? To summarize, I think the best way to summarize it is to go to scholar.google.com and to just type in Maxeler, and one can see over 1,000 results of papers, peer-reviewed research that has been inspired so much by Maxeler's work that they actually used our company name inside of their paper. And so possibly more stuff was inspired, but over 1,000 research publications have been driven by that. And of course, we have a selection of these that we wrote or co-wrote with our partners and clients. and with our university program members. So there is a strong university program with over 150 universities that have used the system. And you can see the publications on our website as well. The modern state of things.
Oskar, sorry, we are running out of very much time. So
yes, 10 more seconds.
Okay.
So the most modern implementation, you can see Static Dataflow here presented last year by Grok, a up-and-coming, inspiring new chip AI company that has published last year that they are using Static Dataflow in order to optimize computations. So the next wave is going to be programmable ASICs, which will hopefully make the programming of these systems a lot easier again and provide another jump in performance. And I couldn't talk about flow without, in Hungary, mentioning Mihai Csikszentmihalyi, who showed us that only when the challenge level is high and when the skill level is high do we achieve proper flow and happiness. And so I'd like to end on the happiness note here, and I'm happy to take any questions.
Okay, thank you very much, Oskar. So we can have time for a quick question, please.
Okay, so,
can you speak up with? Yeah.
Okay, so first of all, being an optimization junkie myself, I'd like to congratulate you on everything you do. So this idea of static data flow analysis and implementation is excellent. However, both experiments on this topic in my head, there was one problem that was constantly coming up, which is basically that whenever you have a problem, a trade-off, basically, that you have a fundamental decision putting in more execution units for a particular function or not to speed up a particular hot part of the pipeline or the graph, basically. Then in a static scenario where every dimension of the data is known, hence the different proportions of different tensors relative to each other are also known. This is a problem which can be optimized. So now I understand that in your case you're focusing on these, that's why it's static. But did you think about dynamic applications? So could you deal, or did you ever try to deal with scenarios when dimensions or proportions are not known and you would need some kind of dynamic adaptation from your system?
Well, every computer system is optimized to a party, or every solution is optimized for a particular data size. You may just not know it. And the question is, how gracefully does it reduce the performance as you're increasing the size of the data? It depends on the computer system you're using and the portability of the code. The more you optimize, the more rigid it becomes to the particular optimization target that you're using. So it's very much the opposite of optimization. What you're talking about is not making it dynamic. You're talking about abstracting away the size of the data. And that dynamicism is the opposite of performance, of optimization. So you have to look at abstraction as the opposite of optimization. And you can do one or the other, or you can have a compromise in the middle somewhere where neither one is going to be really strongly supported. So in essence, yes, you can do both, but then you lose performance and you lose abstraction. If you just do abstraction, you have unpredictability and very bad performance. And if you do optimization, you have very good performance for a particular data set. So you have to look at the computational problem as the amount of data. It's like saying that I'm going to build a general machine to add numbers. You say, but how many numbers? I'm going to build a general machine to move Earth. Okay, now we understand. How much Earth are you going to move? Depending on how much Earth you want to move, the machine is going to be completely different. If you want to move 1 cubic centimeter, that's a completely different machine than if you want to move a cubic ton. So it's really, really important to know how much data you want to move before you build the machine, the implementation, or your solution. When you call a moving company, the first thing they ask you is, how big is your apartment? And you say, well, just move whatever I have. Say, but we can't do that. We have to send a truck. The truck has to be big enough. So you have to tell us how big your apartment is. Then we are going to put together the solution. The same thing is true for computing. You need to tell people how much data you want to move. Then you can come up with a solution, an efficient way, a good way, an affordable way to do that. Now, I hope that makes sense, even though it doesn't really answer the question on how to do what you want.
Surely it makes sense. So I didn't mean to imply that, okay, this is great and the same thing could be done dynamically. So no, I agree your point that restrictions are necessary to enable optimization. So that is clear. I was thinking more about, expanding the number of use cases basically. So it's obvious that the resulting system would be less optimal. However, it could be more generic. So basically my thinking is more along the lines that this could just as well be a fundamentally better way of doing the processing under every circumstances. And should that be the case, then maybe the more generic, albeit less optimal version could still be more optimal than the existing generic solution.
So generally, there has been improvement with the Grok architecture. So that is the next thing I would like to encourage you to look at. I see we are out of time, so thank you very much, everybody.
Thank you, Oskar.
Thank you very much, Oskar.